So welcome everyone to today's webinar. My name is Ari Hakimian. I'm an application scientist here at C-Therm. Today, our webinar topic is Advanced Composites, a key enabler, next generation electronics. And excited to be joined by one of our guest speakers here, Jeff Gotro. Jeff is the president and founder of Innocentrix. Innocentrix provides a wide range of consulting services to the polymer industry. Jeff has over 40 years of experience in polymers, having held scientific and leadership roles at companies such as IBM, Honeywell, Electronic Materials, and more. He's published 5 books, book chapters, including Thermosets, an encyclopedia of polymers and technology. He has also authored and co-authored over 61 papers in technical journals and conference proceedings. He holds 15 issued U.S. patents, and Jeff has a Bachelor of Science in Mechanical Engineering and Material Science from Marquette University, and a Ph.D. in Material Science from Northwestern with a specialty in Polymer Science. So really excited to have Jeff here with us here today. I'm also joined by my colleague Hitoshi Taniguchi, who is a technical specialist here at C-Therm, who will be going over some content later on in the session as well. So welcome everyone. I'm just going to get things kicked off here with a little bit of an intro, a little bit of background on C-Therm, who we are and what we do. So C-Therm Technologies, we are experts leading in the transient space for thermal conductivity testing. Really our goal and our purpose here is for simplifying thermal conductivity testing for the materials of tomorrow. Now, our core instrument platform is shown here. This is Trident. Trident was developed as a modular system. It really brings together 4 of the most prominent methods in transient thermal analysis. The idea behind Trident is really giving you that flexibility to be able to choose the best method for the task at hand. This next quote here, this is from Abraham Maslow. It's one we like to reference, but when all you have is a hammer, everything looks like a nail. And really this symbolizes the idea behind Trident. By allowing you to choose a specific method that is, really designed for the material and the testing conditions that you're looking at, it allows you that flexibility. So you're not trying to force a singular method on a, broad range of materials that maybe it wasn't necessarily designed for. I will just make note of this method selection guide. For those of you who may be new to thermal conductivity, or even, those that have experience but are looking to maybe take a look at what exists out there in industry in terms of options for testing, this is a free resource download. You can get this on our website. And also my colleague Carter, who's moderating the session, will be posting some links throughout today's presentation. So again, a really nice resource to take a look at just to expand your knowledge base on what options exist out there. And before I pass things over to Jeff, one of the things I wanted to mention, related to polymers and composites, specifically here, kind of looking at thermal interface materials. One little example I wanted to share, probably the most common use case that we've seen from where thermal conductivity is playing a role. In terms of the performance metric of TIMs and many of these composite systems, thermal conductivity is, of course, significant. But the thing I wanted to take a look at just very briefly was what's going on with the fillers. I know in some of Jeff's content, he'll be talking about some of these aspects as well. But from a thermal conductivity measurement perspective, the fillers are really what's doing a lot of that heavy lifting. But there are certain considerations to be aware of in terms of optimizing material performance. One of the biggest challenges we've seen in industry is what's happening when your fillers or your additives aren't behaving as intended, whether that's, starting to agglomerate or sediment to one side. This can cause certain issues. From a material perspective, That lack of uniformity can result in uneven heat dissipation, decreasing your overall performance, leading to safety risks. Of course, in like a thermal interface material, that safety risk is the potential for thermal runaway, which is something we always want to avoid. But past that, past just a material consideration, there's also something to be aware of in terms of testing. When you're dealing with something that is not uniform and, let's say, consistent within the dispersion, this can lead to certain bias depending on which methods are used. Different methods will have different evaluated volumes. Some are directionally dependent, others are not, and all these factors can play a role in introducing some inconsistencies and errors in measurement. And one way that we've taken a look at helping groups mitigate this, or at least identifying if there are issues going on with their materials, is a use case called thermal mapping. And this is specifically done with one of our methods on Trident. This is C-Therm's patented sensor type, the MTPS, or Modified Transient Plane Source. And what this essentially looks like is the following. Let's take this sample here. So this is an epoxy with a conductive metal nanoparticle that is dispersed, but as we can tell by just looking at it, it's not that great. But for the case of the example here, what we can do and what thermal mapping really is entails is by taking the sensor. So these green circles are representative of our test location. So by taking our MTPS and placing it at different locations across your material of interest, you can very quickly get a localized readout of the thermal conductivity, thermal effusivity at each point. And then what we can do with this is get an understanding of the overall consistency, or in this example here, the lack thereof that is present in the material. So as a way of a quick internal, R&D tool, this is a really nice way to very quickly pick up on certain issues that may be present in your samples, especially if, your material isn't transparent. If it's an opaque material, you're not able to pick up on those issues visibly, then this is really provides some nice insight. And really what this allows for is that iteration velocity. Again, in R&D, we're trying to go through the paces, trying to find out what are your top candidates, which are your best performers, and making sure they're optimized accordingly. So from my side, that's all. I'm going to wrap up here and really hand it over at this point to Jeff to take us through the bulk of today's session. So once again, I'd like to welcome Jeff to take us into his content. Thank you, Jeff.
Okay, are we on?
Yep, all good.
All right. Okay, so today we're going to talk about advanced composites. And most people don't think about composites in electronics, but we're gonna define what we talk about composites for electronics as we go. So we're going to talk about the definition of composites in electronics. What is this thing called polymer packaging? What are some of the types of packaging? Then what are the polymers that are used? And as we heard from Arya, the fillers are really the key piece of the puzzle in terms of why we look at these as advanced composites. And then when we use fillers, then we get into rheology issues during dispensing of these uncured formulations. So we have to get these adhesives, the underfills, the mold compounds, thermal interface materials in the right location first. And then in the case of most of these, you're going to see they get cured. So let's first talk about what the definition of a composite is. So I looked this up on Merriam-Webster, and it said it's something that's made up of distinct parts or elements. And I thought, whoa, that's pretty good description. But typically we think of carbon fiber or woven fiber impregnated with resin, typically in composite applications. But for electronics, we're going to look at thermosetting polymers, and then fillers such as silica, silver, alumina, boron nitride. And then when we talk about laminate structures, circuit boards and chip carriers, then we use woven glass cloth in prepreg and laminates. So in the circuit board world or chip carrier world, this is much more like what you think of when you think of a composite. Um, and then we're going to show you how electronic materials are highly formulated, and they're polymer based. And we use various different types of chemistries to tailor the properties for the specific application. So let's talk about this funny word called electronic packaging. And when people think of packaging, they think about wrapping and boxes and things like that. In electronics, packaging is the term that's used to encompass all the different ways that we connect the input output from the semiconductor chip to various interconnection pathways. So in this case, we have the silicon die, and then it's through these bumps here, solder bumps, come down to this substrate, and then through the substrate, through the solder balls, and down to the printed circuit board. So we have this whole routing hierarchy that comes from the chip to the substrate, down through through these vias they're called, to the solder ball, down to the printed circuit board substrate. So this is how all these different levels of packaging are enabling the chip to communicate with each other and with other types of things such as memory, capacitors, inductors, things like that. So we've had this packaging progression where we started a long time ago, where, in the old days, if you opened up an electronic, you look inside and you'd see this black thing that had these little wings on it, these gull wings, and soldered down to a circuit board. But then they got smaller, and so then we put the substrate down, put the chip here, and then we wired it down to this substrate. Now, in all of these cases, you can see this teal right here is the die attach adhesive. It's kind of a funny name because once these come out of the wafer, they're called die. And then this teal is a die attach adhesive. So it's a highly engineered adhesive, thermally conductive, electrically conductive on that adheres the semiconductor chip down to this, in this case, the lead frame or the plastic ball grid array. And then to get smaller and smaller, then we took these chips, instead of face up with wires, we flipped them over, used solder balls to connect. And now there's a new packaging type called EWLB, wafer level ball grid array, where we completely take the substrate out and we use high density wiring right here on the top of the chip. So there's all of this interconnect, and it's all pretty much enabled by these advanced composites that are polymers and fillers. And so here's a cross section of what we call a high density interconnect circuit board. You can see on the top, here's the semiconductor chip. It's got all these little connections, these pads that they solder ball down or pillar down to this high density printed circuit board substrate. So this is what's called a chip carrier. And then there's all these little interconnects through multiple layers of this Ajinomoto buildup film. And these buildup films are epoxy and phenolic, epoxy and cyanate esters. So there, again, there's a lot of chemistry that goes into developing these materials. So they have the right electrical properties and they have the right thermal and mechanical properties. And then in here, there's woven glass. So here's where we see this whole composite approach. These materials are highly filled. These have woven fabric in them, and then more layers of this buildup film on the bottom. Um, and so there's a number of different technologies involved: bismuth, triazine, epoxy resins, epoxy phenolics, epoxy cyanate esters, and then these vias can be filled with silver-filled epoxy or silica-filled epoxy, depending upon what kind of performance they need. So very complicated, but highly engineered composites are used in this electrical interconnect world. Now, one of the things when you get into these newer phones, not the first generation 5G is out now, but when we get into the next generation of 5G phones, these circuit boards are going to have an antenna layer built right in them. And so now we have these new polymers that have very low dissipation factor. DF is an electrical property, so that you can have these multiple antenna arrays built right on top of the substrate. And again, we have bismuth triazine resin with woven glass cloth. We have our buildup films. And now we have this chip that's attached to the bottom of this complicated substrate. And then these bumps go down to a main circuit board. So this would be like the main board in the back, in your cell phone. And this structure would be mounted onto the what we call the motherboard on the base of the cell phone. So let's talk about material properties, because everything we're going to talk about in the subsequent slides, we're going to have a focus. So we're going to either work on the glass temperature, coefficient of thermal expansion, the modulus, specifically in the newer packages, the dielectric constant, which is called dK, and the dissipation factor dF. dK is how fast the signals will transverse across the circuitry. The dissipation factor controls how much of the energy is lost. So to get good battery life, you have to have very low dissipation factor. And then we're going to talk a little bit about dispensing and flow of uncured material, and then a little bit about what happens to the rheology when you cure. So one of the most important and common thermosets is epoxy. And this is the chemical structure of epoxy. It has this three-membered ring on each end. And we do chemistry by opening this ring. And it has this OH group in the middle. When you open up one of these rings, you form another OH group. The OH group is good for adhesion. It's a reactive site, so it can do chemistry. It helps when you're putting it down on the surface to wet the surface to get good adhesion. But the drawback is that this OH, hydrogen bonds to water molecules. So if water absorption is really important, epoxy might not be the best choice. There are other materials now that have much lower moisture absorption. And we'll talk a little bit about those very briefly coming up. So there's a number of different resins that are used for these adhesives. A lot of what we use in electronic materials are adhesives or coatings or encapsulants. And so we have a multiple toolbox of resins. So we talked just previously about epoxy resin. Now, when we want to go to very fast polymerization systems, we're using acrylics or acrylate monomers and oligomers, right? And then in acrylates, you polymerize across this double bond. And then we talked a little bit about those chip carriers. And I said, remember, it had bismuth and the cyanate ester in them. This is the functional group of the bismuth. It's got a double bond here. So now we have reactive sites where we can polymerize across these double bonds, and we can make them go very, very fast. So these are what are called free radical polymerizations. And you can initiate a radical, and then they propagate very, very quickly. So this is how you can get systems that cure very quickly within a matter of minutes. And then a really interesting chemistry is a lot of applications we combine these. We put epoxy and these acrylates, so we can build a network first with epoxy, and then we can then initiate these free radicals that polymerize across the double bonds. So we'll have a mixture of epoxy, acrylate, or methacrylate, or bismuth, and we put in this hybrid. And so now you see we have a free radical site on this end and epoxy on this end, so we can tie the whole network together. So everything is chemically bonded. So there's a lot of sort of, chemical molecular architecture work that we do in these types of adhesives. Here's a few different types of epoxies. So if you want higher glass transition temperature, you can use these epoxy Novolacs. The one that's primarily used is this Cresol Novolac. It's got this methyl group here, and it's right close to the epoxy group. And this is nice because it lowers the moisture absorption because steric hindrance around this OH group prevents the water molecule from getting into the OH group. And then this is a different type. Remember, I said there's some phenolics. So this is a different type of curing agent that's also used. And then in pretty much almost probably every cell phone, there's this BT, we call bismuthine triazine substrate. And so it's got this bismuthine group in it. Remember, we said polymerize across these double bonds. Then we have this cyanate molecule. So the C triple bond N is the dicyanate. There's one on each end. And that forms these cyclic rings. So it's called cyclotrimerization to form this really high, rigid, high glass transition temperature network. And then we have our friend epoxy on the bottom here. Now you notice in all of these, they have reactive groups on each end, right? And so now by tailoring the ratios and the types of material you put together, you can form some very interesting and specifically tailored glass temperature, modulus, electrical properties. So the cyanate ester is really nice now because it forms these three-membered rings, so we get a really high TG. But the drawback there is they're brittle, and there's ways that you can fix that. But if you look at this, there's very little OH groups on here. In fact, there's none. There's very low polarity. So these have very low dielectric constant, very low dissipation factor. Now you say, well, Jeff, there's no polarity. How do they have high moisture absorption? Well, it turns out the way these chains sort of polymerize and pack, there's space in between the chains. So if you just use straight cyanate ester, you can get high moisture absorption because the water kind of wiggles in between the chains. But if you remember from that last one, the last slide, we talked about the BT system. We had epoxy, we had cyanate ester, and we had bismuthine. Well, the bismuthine and the epoxy kind of wiggle around in and close up the spaces. So we get this nice property from the cyanate ester, but then we kind of fill in the space with these other materials to lower the moisture absorption. So again, this shows you how we do molecular, sort of what I call molecular architecture. And now the newest thing, as we talked about, driven by the 5G cell phones, are very low dissipation factor laminates and prepregs. And we have PTFE systems. So they have PTFE, which is polytetrafluoroethylene or Teflon. We have PTFE with woven fiberglass. We have PTFE with ceramics. But PTFE is very difficult to work with. It has a very high melting point. And when it does melt, it has a viscosity of lead at room temperature. So what people have done is they've taken this AGC, Asahi Glass Company, has formed this modified epoxies, and they have this line of material called meteor wave, and they have very, very low dissipation factor, and they have relatively good dielectric constant as well. So these are used to make these very low DF laminates. The other thing you say, well, what's the DKDF of glass? Because these are highly filled with glass fabric, much like you would see in a composite application, typical composite application. But you can see here at 1 gigahertz, the glass has a very low dissipation factor. So the good news is you can lower the dissipation factor of the resin, and you already put it in a pretty low dissipation factor glass cloth. So a lot of them use this NE glass because it has the lowest of all of the of the glass is available. And you can get this in various styles of woven glass. And so here's what one of these stacks looks like, right? So you can see, remember we showed you on the earlier slides, we have these stack ups of the outer layers. Well, this is a what we call here a through via. So the via goes from the top surface down to the inner surface inside of this carrier. And these are drilled with lasers. So you have to drill through the resin, you have to drill through the glass. And then there's multiple thicknesses of glass. So you can see up here in the vias where these layers are really thin, they use very, very fine woven glass. Down here in the core, then they have much thicker. So these in this cross section, where right where my arrow is, the weave is coming out at you, and then these are the yarns that are going in the Y direction, and then the yarns, these ovals that are coming out at you. But you can see various different sizes of fillers or of the glass cloth from the center core out to the fine surface on the outside. Now, let's go in, let's talk about fillers. And we're going to spend a good amount of time here on fillers because, as Arya said in his introduction, fillers really do a lot of, and I like his term, heavy lifting. And we're going to talk first about conductive adhesives, where we need to have the adhesive conduct electricity. So in order for us to get electrically conductive, we can use silver flake, we can use silver powder, or a combination, which I coined the term raisin bran. Those of you who have eaten this cereal, you can see that it's got flakes and it's got raisins. So here's the flakes that are used for die attach adhesives, and they're plate-like structures, right? And then here's powders on the bottom here, and they're very nice and spherical. So you can think about if we have these encapsulated in a resin, the spheres are going to roll past one another, and it'll flow, relatively easily. But if we have these plates, and they start trying to flow, they're going to have to tumble and they bang into each other. So in order to help get electrical conductivity, you need to have these plate-like structures, because I'll show you in a minute, these need to be very close to each other to get electrical conductivity. So what you can do is you use this structure over here on the lower left that has a combination of these silver flakes and spheres, hence my term raisin bran. And the reason that this is important is because if you have not enough filler in there, so this cartoon on the left, too much yellow, which is the bulk matrix, you don't have a pathway. So then you need to get to the percolation threshold, as shown in the right-hand side of this cartoon. And now you have a path from one interface to the other interface. But in order to get electrical conductivity, you have to have electron transport. So particle needs to be very close but not touching. It turns out that this electrical conductivity is really driven by electron tunneling. So we want large surface area so that we can get, close but not touching. And, silver flakes are the most common, and we need to get the filler loading above the percolation threshold. Now, let's switch to non-conductive, where we need them to be electrically insulating. And in this case, fused silica is widely used. It's available in high purity, has good chemical resistance, and a lot of times it's used because it has low coefficient of thermal expansion. And as a filler, you can use this to do two things. You can provide modulus, you can provide some of the coefficient of thermal expansion. Spherical fused silica is the most common filler. It's used in high filler loadings up to around 65 weight percent. And because of we talked about before, the spherical geometry has a smaller impact on the viscosity. But one of the things that's super important about all these fillers, and I didn't touch on it in the case of time, but surface treatment is key. So the silvers are surface treated, and now the silicas are surface treated. Multiple chemistries are available, and these allow to control rheology, and then they also couple the resin to the filler. Um, and then you can treat the fillers so they don't agglomerate. Because remember, Arya was talking about agglomeration. That's a bad thing. So you can surface coat these fillers so that they don't agglomerate. And then you can get to very high filler loadings, and we'll show you how you can use bimodal, trimodal distributions to get the very high filler loadings. So one of the things that fillers are primarily used for is lowering the coefficient of thermal expansion. So on this plot, we have the coefficient of thermal expansion, and then on the y-axis here, we have the filler volume percent, right? And you can see here for silica, you can get pretty much a linear decrease in the coefficient of thermal expansion. But you have to add a significant amount, high volume percent of silica. Alumina is a little better. Diamond gets you there much faster. And boron nitride gets you the lower CTE. But boron nitride, though, is platy. So it has this plate-like morphology, where silica, we saw earlier, is spherical. And the diamond kind of has this little spherical type of, but they're very small. And then alumina is kind of in the middle, right? But the point is you use these fillers to do control of the thermal expansion. In the same way, you can use fillers to increase the thermal conductivity. So in this case, silica is not very good to increase thermal conductivity, whereas boron nitride, the square here, very efficient at increasing the thermal conductivity. So one of the things you could say, well, let's use boron nitride because you can, number one, it decreases the CTE nicely. Two, it increases the thermal conductivity, right? Well, that works to a point, and we'll show you why you have these limitations coming up in a minute. Right? We're going to talk a little bit about thermal interface materials, and a little bit different here is the same kind of cartoon we saw before. You need to get this percolation threshold, and then you also need to build these 3D, 2D networks. And thermal conductivity is driven by phonon-phonon coupling or vibration. So in this case, for thermal conductivity, you need good particle-particle contact. And again, the same kind of thing we talked about earlier, large contact area is better. And you need to get the filler loading above the percolation threshold. So what's interesting is in the electrical, you need to get them close, but not in contact, i.e. you modify the surface of the silver with some proprietary type of treatments. In this case, you want them to touch. So you need then to have the surface here to get good particle-particle contact. And here's the problem, right? And you go, oh man, that boron nitride looks great. But boron nitride is platy, and silver flakes are platy. And what we have here is these are normalized viscosity as a function of volume fraction of loading. So as we increase the loading, we get this, what I call this, the viscosity penalty. So if you see here plates, which would be boron nitride and silver flakes, you get this very huge increase in viscosity at relatively low volume fraction of filler. Whereas the spheres, as you can see, they roll past one another. You can get out to, pretty much greater than 0.5 volume fraction of the spheres. So you can get a lot more loading before you get into this very, very high viscosity regime. So that's when you're formulating, you're looking at the chemistry, you're looking at the filler loading, you're looking at the aspect ratios of all the materials that go into these highly formulated composites. The other thing is once you get silica filler in there, let's just say we'll use silica because that is the one that has the lowest, what I call the viscosity penalty. But when you load it up with various levels of silica filler, even then the viscosity goes up dramatically. So in this case here, the yellow curve at the bottom, you notice that at different shear rates, the viscosity stays the same. That's just the resin. There's no filler in it. Then we started adding the filler into it. Then you start getting this viscosity increase. And this is on a log scale. So once you get up to 60 volume percent filler in silica, the viscosity is really big. And then you build this thing called the yield point. So how do we get these very high filler loadings? So if you just use all of one size, you can get one filler loading. If you just use all of the big size, you can get another filler loading. And as an example, if there's any material scientists in the audience, this is what's called a face-centered cubic. It's the hexagonal closed pack. It's the tightest packing you can get for these uniform spheres, and its packing volume, packing density is only 74%. So what you can see in this space filling model is there's lots of space in between here. So how do we get higher than 74% filler loading is we go through this bimodal distribution. So we can get to this maximum by putting big particles and then little particles in between. And so what you can do is you can change the ratio is the diameter of the large, the diameter of the small. And what you can do then is come up with different ways to put the little spheres in between the big spheres. And this is all in this paper that's all this stuff has been worked out. And that's a great paper if you're really interested in this stuff. But here, remember that cartoon went up and down? Well, in real life with data, I mean, you can see that this is the fraction of the filler, and right here around about 0.3, right? So packing density occurs when the volume fraction of the smaller particles is about 0.3. Now, these are all for ideal mono-sized powders. Now, as I showed you in those SEMs, none of these powders are mono, but we use this as a really good estimate on how to start to build these formulations. And then if you then want to increase the ratio, so this is bigger particles are 5 times the size of the little particles, you can get the pretty high packing density with these bimodal fillers. Another way is to use trimodal fillers. And so this is an example from an epoxy mold compound. That's the black stuff that you see around the chips. So, and you can see here, there's big particles, medium particles, little particles, and they have the mathematics has all been worked out. So if you have your biggest particle as a radius of r, then the next generation down is going to be 0.41 times that radius, and the next generation down, the one that'll fit in here, is 0.225 r. So you can actually choose a big particle and then go get the next generation and the next generation. And I got this cross section, and I got this SEM picture from Sumitomo website. I actually did the math, and it's really close to this R.4, 0.2. So this is used in commercial products. Now, the next thing we need to think about is resin curing. So when you start this formulation, you mix in all these components. So we talked about different resins, and we didn't really talk about there's things called hardeners, there's adhesion promoters, there's wetting agents, there's other additives that the formulators put in. You put that all in this formulator, in this resin formulation, you mix it all up and you get this low viscosity liquid. But then you put in your fillers and you mix them together, and then you have to dispense them. Then once you get them dispensed, then you cure them into this cross-linked network. So in this cartoon, we show, starting materials, small, really small molecules, and those turn into larger, longer branched molecules. Then they start to cross-link. So all these these are all pretty much linear chains. And then when you start to what we call cross-link, then these chains start to link together and they form these longer chains. And if you remember, when the chains get long, molecular weight increases, the viscosity goes up dramatically. So now we have the fillers increasing the viscosity, and now we have the resin, as it's curing, increasing the viscosity. All right. So we have a lot of different process options when we're using thermosets. So we start with these low viscosity monomers and oligomers. We can tailor the properties by the choice of what we put in our initial formulation. We can actually control the viscosity by putting these little diluents in. So they're low viscosity molecules that react into the growing networks. Then we can partially cure them. So we can take them kind of like a little bit of the way, not all the way cured, so that they can be potentially have film-like properties. But then when you put them in the process, like in a lamination press or as an adhesive, you cure them after you put the semiconductor chip, you glue the chip down, they can still flow and cure with additional heat. Then once we have this fully cured network, all the molecules are pretty much, 99+% of the molecules have reacted, then they don't flow anymore. They can have a really nice glass transition temperature depending upon what chemistry you choose. And the reason these are used in electronics is because they're very thermally stable. So if you have this glass transition temperature of 175 C, 200 centigrade, you're going to need to get well above that to solder. But the good news is these are cross-linked networks, so they'll have a glass temperature, they'll soften, but they have very rigid networks that don't move. So they're thermally and dimensionally stable. And then, like we talked about, you can control the coefficient of thermal expansion with fillers. So one of the issues is when we dispense is we have this curve, and we saw a little bit of that when I showed you the silica data, is we start at a high viscosity at a very low shear rate. And then as we increase the shear rate, then the viscosity drops dramatically. So we dispense out here in this high shear rate range where the viscosity is very low. But then there's this thing called yield point and shear thinning where the particles interact. So this is an example of a die-attach adhesive, this picture up in the right corner here, where we've printed this, what we call a snowflake pattern. And so when we print these patterns, we dispense down here at a very high shear rate, up in the order of 3, 4, 500 reciprocal seconds. The viscosity is low. We can print the snowflake pattern. But then when we stop dispensing, then the shear on the surface goes right back up this curve very quickly, by the way. And now it has this shape that maintains after it's dispensed. So a super important piece of the rheology is because we can put the adhesive where we want it, and then it's not going to run and dribble out all over the place. It'll stay in place. So this filler loading is super complicated in terms of what happens. I'm just going to go through this very quickly. Is when we have these fillers, if their particle interaction isn't controlled, you have this network structure where all these particles are interacting, and you have this network. And then if you apply shear, sequentially, nothing moves because these networks, the particles don't allow flow. You can see down here we have the resin only again. Remember, this is just the resin base. There's no filler in it. So very low viscosity and no shear rate dependence. But then when you get to this dashed line here called the yield point, then the shearing forces start to break up the network and form aggregates. And then at higher and higher shear stress, this is stress now. We do a little bit different experiment, but I want to just use this to illustrate the point. We start breaking up these aggregates, and then when we get out to very high shear stress or shear rate, we have discrete particles. So that's why when you saw those viscosity curves, they all start high with high filler loading and they come down and they sort of level out. So the resin is Newtonian, which means it doesn't have any shear rate dependence, but the sheared behavior is of the filled materials completely dominated by particles. So one of the things that you should take away from this webinar is that one of the things that we spend a lot of time when we're formulating these complex composites for electronics is the rheology is a key piece of the product development process to get the flow and everything right. And then we have to add in what's the right filler for thermal conductivity or coefficient of thermal expansion, and then, electrical properties and mechanical properties. And then we have to cure this material, right? So here's an example of epoxy that has these epoxy rings on it. And these has an amine group on each end, right? And this amine reacts to this epoxy to open the ring and polymerize. But if you cure this material at 129 C isothermally, so you just put this in a process where the temperature is constant, you can see that the viscosity stays low for a while, but then it rises dramatically. And this rise dramatically is when, remember I told you that you're getting branching and the molecular weight is increasing, but when you get to this point, when all those chains start to connect or cross-link, the viscosity goes up very, very quickly. So you can see on all these different curves at different temperatures, then you have different amount of time, and this is in seconds now, log in seconds. You have different amount of time to get the material to flow, get in place where you want it, and then the chemical reaction is going to cause it to not flow anymore. So when the viscosity gets up into this range, where these curves essentially go vertical, you're not going to get any more flow. So the process window essentially stops. Then if you do it non-isothermally, i.e. you're in sort of a press or some sort of a composite molding, right? You can ramp the temperature. So you ramp the temperature up to the cure time. And by ramping, you can control, in this case, I'll show you, you can control the minimum viscosity. So the numbers along the bottom here are the heating rates to 175 C. So in this case, we started at room temperature and we went up, we ramped up to 175 and then we held it. And you can see here that if you ramp very quickly, then you get a very low viscosity, but it cures really fast. So the viscosity may be really low, you can get it into the mold, but it may stop before it flows all the way in because it's curing too quickly. In this case, the viscosity at slow heating rate, the viscosity is very high, so it may not flow where you want it. So what the process engineers and the formulators work on is getting the process to work kind of right where you need it. And in this case, this is work that I did when I was at IBM, and we developed a process that worked kind of between 8 and 5.8, right here in the middle. So we had a nice, pretty decent flow window, which we called it, so the resin would flow. We could get it where we wanted it, and then it would actually fully cure. And you can see here, all these curves come up pretty much to the same endpoint, right? Which means that we get the same level of cure independent of how fast or slow we move it around. Because the flow moving around, the rheology, is governed by the thermal transients, the heat transfer, and then the level of the cure is driven by the chemistry. So here's how you can, that's why we call this chemorheology. we modify the chemistry, and then we modify the thermal to get the right kind of flow. So in summary, electronic packages require some sophisticated polymer-based materials. We're fortunate that over the years, we have a wide toolbox of thermoset chemistries available. Polymer composites are used because we can get to those tough material requirements, so electrical, mechanical, thermal. And then filler plays a key role. And pretty much all of these composites used in electronics are highly filled. So there's all kinds of types of fillers, customized surface treatments are available. And then one of the things that you really have to do is use rheological methods, and chemistry and thermal analysis methods like DSC and DMA and TGA, TMA. So all the thermal analysis is the polymer characterization. And then you need rheology to characterize the uncured materials so you can get them to flow. And then you need rheology to look at the chemorheology during the curing, so you can understand the insights into flow and the process window. So with that, this is my contact information. I think you'll be provided this when we're done. And then maybe some of you are already on it, but I have this really interesting polymer innovation blog.com where I write all kinds of interesting information on polymers, polymer innovation. So thank you for your time, and we can open it up for questions.
Right. Thank you, Jeff. Before we move on to Q&A session, I have some presentation on my side, which I'd like to quickly share before we move on. So just quickly share my screen here. Jeff, if you could stop sharing the screen for a moment.
Got it.
Okay, awesome. Thank you. All right. Okay, so again, thank you, Jeff, for the insightful presentation. Very interesting to learn about different considerations when it comes to setting up these composite materials and different properties that you have to look out for. You briefly touched on this at the end, but there are some material properties that you can access to different thermoanalysis techniques. So I'd like to give a very brief recap on those properties and how you might be able to measure them. So the first off, one of the first properties you mentioned was the TG, the glass transition temperature. And very broadly speaking, this is the temperature at which the amorphous materials like polymers, rubbers, or even glass change from a rigid glassy state, hence the name glass transition, to a more rubbery, flexible state. So here we have illustrated videos of this rubber ball being dropped at two different temperatures, one above the glass transition, one below. And you can see that the material properties are drastically different from that of being rubbery, bouncing material to being rigid and less bouncy, as you can see here. So one of the common applications of TG as a property is the rubber industry, since TG determines the minimal operating temperature in which the rubbers can retain elastic characteristics. So obviously, when you're designing these kind of materials, you want to keep this in mind, since once you go below this glass transition temperature, your rubber will no longer have this dampening effect, and it would just be rigid, solid block of wheel. And especially in polymer engineering as well, when we are seeing these plastics and polymers and epoxies, like Jeff mentioned, being packaged into different systems, whether it be electronics or even automotives in some cases. And plastic below this glass transition, on the flip side, will retain this rigid characteristics, and is great for structural support and providing mechanical strengthening. And one of the most common methods that measure this property is differential scanning calorimetry, or DSC. An interesting data we obtained from Ryaku's DSC Vesta, you can see here, is fluoropolymer O-ring being measured after being held at 250 degrees Celsius for different durations. So as you can see, as the hold durations increase, we see a shift in the glass transition temperature into a higher end of the temperature. So this raises some safety concerns if you're using these kind of materials for a long period of time at different temperatures, but it is also crucial for setting up a safety data sheet or technical data sheet when you're considering the maximum operating temperatures for these kind of materials. If you'd like to run a simultaneous TGA DSC analysis of your material, something like STA, such as Rigaku's STA Vesta, is quite ideal for these kind of applications. So with STA Vesta's enhanced DSC sensitivity and TGA resolution, we can detect a glass transition of this PET material around 73 degrees Celsius with some mass loss. This is about 10 micrograms of mass loss happening, which is associated with volatilization and some trace gas off-gassing as the sample is being heated into 100 degrees Celsius. Another very important material characteristics that Jeff mentioned during his presentation was a coefficient of thermal expansion, or CTE. As a background, materials typically expand as the temperature increases, and this is called a thermal expansion of a material. There are two common examples of thermal expansion in real life, as you can see here. So for those of us in a hotter climate, you can see some structures like railroad in this case being warped due to high temperature increase during the summer, causing these kind of distortion in the structure. Or even for those of us in a colder climate, like here in Canada, we see a lot of cracks on the road due to rapid expansion, increase and decrease in temperature, causing these kind of cracks to happen on the road. And coefficient of thermal expansion is a value which describes how much this expansion occurs. So if a CTE of a material is very high, it means that it expands a lot compared to materials with lower CTE. Now, CTE is a very broadly applied characteristics, but some of the common CTE applications that we are seeing today includes electronics or semiconductor packaging, since when you're dealing with highly composite materials or highly packaged systems, mismatching CTEs of these components will cause stresses or cracks over repeated cycling, especially in electronics where temperatures fluctuate quite a bit during its operation. And also in aerospace and aviation, where these equipments and aircraft and spacecrafts experience extreme temperatures depending on how it's being operated. And one of the most common methods to measure this property is thermomechanical analysis, or TMA. And perhaps it's one of its greatest strengths is how it's more flexible when it comes to sample preparation, as opposed to some other methods that measure CTE, like electrometry. Especially with Rigaku's TMA 8311, you can measure pellet-like samples like this one by using a stage method, as you can see here. So even though its thickness is quite on the small side, it's about 2 millimeters in thickness, we were able to measure its thermal expansion, as you can see here. This is the plot of length increase over temperature, and you can see a rapid increase around 140 degrees Celsius, characterized by a glass transition of this material, and around 110 degrees Celsius, we can see a softening occurring as from the effect of temperature increase. Now that's all in terms of my technical content, but I'd like to give us a moment to kind of give a happy holidays and happy New Year's for 2026. Here are our main equipment with a Santa hat. I thought it would be a little bit silly for this slide over here, but thank you everyone for joining us for our webinar today. I wish you a very a good time for the holiday season that is coming. Yeah, I'll hand it off to Aya for some more announcements and future collaborations we have in store for our webinars.
Awesome. Alrighty, folks. So yeah, we're gonna get wrapping up here. Just a few little tidbits on the outro. So, if this type of content was of interest, we do have a variety of past webinars that you can check out. Also, a technical library which features a lot of the content that is presented there. You can take a look into that in further detail. As Satoshi touched on, so the Rigaku product line for thermal analysis is one that we represent here in North America. We also work with Metrovid for their line of DMA systems, as well as offering full service testing capabilities through our TAL group. So again, whether you're looking at instrumentation or potentially looking to have testing performed. This is something that we're certainly happy to assist with, and definitely feel free to reach out with any inquiries. That all being said, if you'd like to know more on any of the product lines or any of our offerings, we do offer free technical consultations. These would give you a nice one-on-one chance to really go into specifically what you're looking to do, chat with us about what we could offer in terms of a solution for you. And again, we're happy to set these up. And of course, for those who, you like what you see and maybe you're just looking for some budgetary information, I know we're getting close to the end of the year, but for those folks maybe looking to plan for things in 2026, definitely feel free to reach out. We're happy to provide that. And for the folks on the line that are coming from the academic sector, I did just want to note about our academic support program on our Trident thermal conductivity instrument. You can see here some of the benefits of having this added in. So if you are from the academic sector and you're reaching out with any inquiry, please make note of the academic support program. We'll be happy to apply that to your inquiry. My last request here is for those who aren't already doing so, please give us a follow on LinkedIn. This will be where we put really all of our latest and greatest content, upcoming webinars, blog posts, etc. So if you're looking to keep up with what we're doing, it all goes to LinkedIn first.